Hello, my name is Sterling, and today we're going to be looking at a fluid dynamics problem. Our problem statement states that water is pumped from the large tank shown in diagram A. The entrance to the pipe section is sharp-edged and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and actual head rise is provided in the pump specifications as is in diagram B. And then we need to find the volumetric flow rate for the system, show that the observation is fully turbulent flow. That's correct. And if the pump is 70% efficient, we need to find how much power must be supplied to the pump. So first off, then we know that HP is 20 minus 2,000 Q squared. We'll call that equation 1. And we know right here that that is Z1 equivalent to 6 meters. Our diameter is 0.07. Our length is 2 meters. And we know that area is pi d squared over 4, which is pi 0.07 squared over 4, which becomes 0.00385 square meters. And we also know that for cast iron, our pipe surface roughness is 0.26 millimeters, which is 0.026 millimeters, which is 0.26 times 10 to negative 3 meters. And for sharp edge, our K value is 0.5 from figure 8.22. And then now we want to use the energy equation so we can use the values out of that to find our Q. So we have P1 over gamma plus V1 squared over 2G plus Z1 plus HP, which is the head rise for the pump, over P2 squared over 2G plus Z2 plus HL. Z2 is at 0, so we know that P1 is equivalent to P2, which is equivalent to atmospheric pressure, so this also becomes 0 on both sides. Velocity at 1 is stagnant, so that is also 0. So then this equation we can reduce into HP equals V2 squared over 2G minus 6 plus HL. We'll call that equation 2. Now to find our HL term, that is HL major plus HL minor, and HL major can be found by using F times L over D, V squared over 2G. And we know that HL minor is K V squared over 2G. So HL minor, we know that K is 0.5. And HL major is F times length is 2 meters, diameter is 0.07 meters, times V squared over 2G. So then adding up these two terms, then our total head loss can be written as F times 28.57 V squared over 2G plus 0.5 times V squared over 2G. Now for F, we can find that by finding the relative roughness, which is epsilon over D, and that from earlier, our cast iron we know is 0.26 times 10 to the negative 3, and D is 0.07, so this is equal to 0.0037, and if we look at a Moody diagram, we know that the flow is turbulent, and looking at the roughness line for 0.0037 where it plateaus, that is at estimated at F to be 0.027. Okay, so now that we have that, then we can find HL to be 0.027. We're plugging it into this equation up here. And that becomes so this is our two HLs. Then HP, which is equation 2 right here. HP becomes V squared over 2G minus 6 plus 1.27 times V squared over 2G, which also equals 2.27 times V squared over 2G. And this is one HP equation that we have right there, and we also have this equation, and we know that Q is V times A, so Q squared is V squared times A squared. So when we set the two HPs equal to each other, then we get 2.27 times V squared over 2G equal to 20 minus 2,000 V squared A squared. And then plugging in A for 0.00385 for A, then we get 0.0296 V squared. So now that our only missing variable is V squared, then we can solve this, and then we end up getting V to be 11.2 0.7 meters per second. So for part A, we needed to find Q, and Q equals V times A, which can be written as 11.8 meters per second times 0.00 385 meters squared. Then Q becomes 0.045 cubic meters per second. For part B, we were asked to show that the observation of our system is fully turbulent. So we can do that by finding the Reynolds number, which can be rho Vd over mu. In our case, rho is 999 cubic kilograms, or kilograms per cubic meter, times V, which was 11.7 meters per second, and D, which was 0.07. Mu for water is 1.12 times 10 to the negative 3. And then from this, then our RE number, Reynolds value, is 730,518, and this is greater than 2,000. And if your Reynolds number is greater than 2,000, that means that your flow is fully turbulent. So this proves that the flow is fully turbulent. And then for part C, we're given that pump efficiency is 70%, so that's 0.7. And then we need to find how much power must be supplied to this pump. And we can do that by finding the power, which is represented as rho GQ times HP. That can be written as HP, which is we're gonna plug in 0.045 for Q into this equation. So that's equivalent to 16 meters, so we can plug 16 into here and then get PF equivalent to 7,027 watts. Now to find power required, we use the shaft work equation, which is W dot shaft equals PF over efficiency. So that's 27 watts over 0.7, and that is 10,038 watts, which is also about 10.04 kilowatts. And here's my signature. Thank you.